Okay. All right.
Daryl would. Here's the biggest question. I want to see what you think. Who do you think was the one that gave Daryl the note? He was locked on.
I don't know. That's a mystery.
I think it was White, White's ex-wife, or it was Jesus.
It could. Those are.
I think it was.
I would not be surprised if it's any of those. All right. Clock is running. Clock.
Do you taught that your physics 2 class too?
Mm-hmm.
Okay, and you teach physics 2 in the,
I teach physics 2 in the morning. Yes.
in the fall?
No. Well. So for here's the current events for the question: am I teaching 214? I teach 214 in the spring. So in the morning, we've got 214. The only other time of the year that 214 is offered is in July. So for second summer session, if you're interested in taking 214, and I am teaching it, it was officially decided this morning. So I'll be here in July, and you can take it then. If you don't want to take it in July, then you got to consider two more things. One, you got to wait until the following spring, so your brain all that knowledge in your head decays with time. The other thing is that there is a high probability that I won't be here. Dun dun dun. Yes. Negotiations for continued employment are still going. I just won't know for sure for about another month or so. So take it for what I know. Jaws are dropping. So the one thing that I will suggest, as of right now, if you want to take 214 from me, take it in July. If you've got friends who say, I want to take Physics 213, you tell them you got to take it in June and July for 214, and then because then, as of right now, the probability is high that I won't be here. So it's all about money and working stuff, and it's a long story that if my blood alcohol content was sufficient level, I would tell you everything. But since it's not, we'll be civil about it and just say, honestly, when the fall, actually, it may not even be decided until like even April or May. But it's one of those things where people are still, we're talking. So that's it. All right, let's get started. What we're going to do is we're going to jump into this. Make sure everything's going. And we're going to do one example. Oh, and a couple of announcements as well. The no tutorial tomorrow. Baseball is tomorrow. It's the first day of baseball, so we don't have class. Now, for other departments, I have no say in what they do. What does that mean for tutorials? Right now, the tutorial from a year ago or so has been posted onto YouTube, as well as the lecture from Tuesday. Also, I've sent you, the second link is the better link to the Google Drive. Two emails went out today, each basically saying, here's a link, click on the link, and it takes you to my Google Drive. The first link only has 2 semesters of videos. The second link has all of the videos. So you can use the second link. Let's see, what else is going on? So the tutorials are up, lectures are up, Google Drive is up. One of the tests, all the versions for that one test, the summer test, are now up. If we have enough time, and who knows if we do or don't, I've printed out a copy of one of the tests from the summer, and if we got enough time, we'll start looking at it. If we don't have enough time, on Tuesday, we'll just do a big review and deal with that. Also for like SDS students, announcements and stuff like that, testing locations and stuff will be announced on Tuesday's lecture as well. Right now, this is similar to problems 4, 5, and 6 on problem set 3. You have an inclined plane. You have an object that has an initial velocity of 10 meters per second. Question: what is the time when it hits the bottom? Does it hit the bottom at all? Or does it come to a stop? What is the velocity if it does come to the bottom? And that's really all I need. Now for problems like this, what we're going to do is we're doing this inclined plane and then we're doing Atwood's machines, which will be on the test. The similarity with these things that I'm showing you right now are that those 4 steps. Right now, this is a fish. If you remember the 4 steps, you now know how to fish. The first thing that you do with a problem like this is find your normal force. So to find your normal force, you got to label forces. This is the mass. Mass is 5 kilograms. In the inclined plane problems 4, 5, and 6, I'm the one who wrote the problems. None of those masses stop. They all reach the bottom of the slope. Problem 5 is slightly interesting, but you'll figure it out. Now, when I draw the force diagrams, for stuff like this, I've done it so many times that I don't write these and then derive them. I've done them enough times where you can just write them like that. So with these force diagrams, that's the velocity vector. Notice how the velocity, some people are picky about it. I'm not picky about it, but it makes it a little more obvious to me. Velocity is not a force vector, so it does not go on the force diagram that's attached to the mass. That's the normal force, and that is the friction force. Friction force always opposes velocity. Had I given this an initial velocity that was up the hill, then velocity would be up and friction force would be down. So now, so that's the force diagram that we're dealing with. So what did I say for step 1? Find the normal force. That's the first step. Now, in some of these cases, there is friction. In some cases, there's no friction. For everything in the problem set, I want you to discover normal force and state there is no friction force if mu sub k is 0. I need you to go through all the steps because on the test, when you use Atwood's machine, there will be friction. So just get into the habit. So normal force. Now what do you do when you do normal force? You sum the forces vertically. For all, well, not technically all 9 problems on the problem set, but for the flat surfaces, inclined planes, and the Atwood's machines that do have surfaces, you do have to figure out normal force. The sum of the forces in y in this case are 0. Why is the sum of the forces in y 0? There's no movement in this plane. There's movement in this plane, so movement in plane sum of the forces is ma. But if there's no movement, now technically it's if there's no acceleration, but there is acceleration in all these problems that we're setting up. So if there is motion in the plane, you slap that equation down. If there's no movement in the plane, you slap that equation down. There's no movement in the y, put that one there. How many forces in y are we dealing with? 1, 2, 3, none, insufficient information. 2. Which 2 are they?
Force normal and gravity in the y direction.
Correct. You're wrong. He said, now, don't laugh at him. Do not mock your fellow students. Only I'm allowed to mock your fellow students. I get personal about that. So you said friction force. What was the question? What are the vertical forces? Is the friction force a vertical force? No, it's a parallel to surface force. So you got to burn your hand a little bit, otherwise you don't learn. Better to make this mistake in front of 120 people right now than on the test next week. So, and no one look at him. He gets very skittish about people looking at him. This guy in the checkered blue and white shirt. So the sum of the forces in y, and as our, well, hi. Hey. As our friend in the middle said, the forces are normal force and FGY, which is mg cos theta. Now the actual sign, truth be told, is kind of important, but not deeply important. Which ones have the minus sign in front? Both or just one or none? Just one. Which one? mg cosine theta. And why is that? Technically gravity is down. The mg cosine theta is down. When you do this, the mg cosine theta is down. Now, question, and this is me asking a dumb question, so I'm hoping that there is a slight touch of insolence in your voice for me asking such a dumb question. Well, why have the negative sign there? Isn't g negative 10 anyway? What's the Eschenberg answer for that? Ooh, what was the rant that I said about negative signs? That they're blank and can't be trusted. They're tricky, shifty, can't be trusted. You need to have them out front. What we do is we let logic dictate the pluses and minuses. We don't let the incorrect statement or the incorrect part in that question was that in Eschenberg's class, G is simply a magnitude of gravity, and it's 10 meters per second per second. So the minus sign was decided by you because it was down. Now, if there was a function that used G that was up, and you said up was positive, well, it's got to be positive because it's up. But if you had G is negative, you would have to have a negative sign to cancel the negative with G, and then you've got all sorts of chaos running through your equations. So simply just having a plus for up or negative for down makes things more simple, in my opinion. So this is the normal force is mg cos theta. That's the first step. Is F sub n always mg cos theta, or at worst, or probably at best, mg in the case of the flat surfaces? No. Problems 1, 2, and 3 have external forces. And there's an external force in addition to gravity. So what the tutorial does is it goes through all those steps about external forces affecting the normal force, and you get to see how they propagate. So it is not always assumed that it's going to be like that. Step 2. Find the friction force. Now, the object is moving. What is the value of static friction? What's the static friction force in this? 0. Why? Because it's moving. If the object is moving, there is no static friction. If the object is moving, if the object isn't moving, there is no kinetic. The relationship between friction force and normal force, since it is moving, you use the coefficient of kinetic friction. What are the units of kinetic friction, or coefficient of kinetic friction? There are none. What'd you say? I'm curious, you were talking, I was talking, oh, and what did you say if I was talking about the normal force? What are the units of normal force? What you just said 30 seconds ago, which was what? Okay. No, I'm sorry. Hold on. So let's ask a few more questions. What are the units of force? Newtons. If I said you're not allowed to utter the word Newton, give me the units of force. You can speak up. Fill the room. What are you going to be? A doctor? Do you want your doctor to say, I think you have the flu? No, you want your doctor to go, you got the flu, I'm going to fix that. So we're working on confidence here. So the units are kilograms, meters per second per second. And how do you get those units? What are the two values when multiplied together? Excellent. Mass and acceleration. What are the units of mass? Kilograms. What are the units of acceleration? Meters per second squared. Okay. If you haven't figured it out, I'm insane about units. Having the ability to manipulate units makes your professor happy and helps you succeed in my class. Because it really does help you work physics problems out, to have that knowledge. So this becomes mu sub k mg cosine theta. All I did was take this, plug it into there. The mu sub k is out front. Notice I have not plugged in anything. If you are a plug-in chugger, I will find you and I will take your GPA and make little squeaking noises as it is slowly flayed. For those of you who are future surgeons, you know the word flayed. So, and she's looking shocked in the front row. Plug-in chuggers do not make good physicists. They don't make good mathematicians, chemists. What I'm trying to do is instill a very valuable skill. Physics is not about crunching numbers. Physics is about understanding the world around us and generalizing it and applying equations to it. Not really interested in the numbers. Why do you think I say gravity is 10 instead of 9.81? Because it's not about the numbers. 10 works awesome in making the numbers work out. So that's the friction force. Step 3. Find A by summing the forces in X. So summing the forces in X. So Walking Dead fan, how many forces in X am I dealing with? Are you a Walking Dead fan too? Because the question said the Walking Dead fan.
Repeat the question one more time, please.
How many forces in the horizontal am I dealing with here? All right. You're incorrect on 2 fronts. 1, you answered it in the form of a question. 2, you got the answer wrong. The person in the back who said 2 with confidence is correct. Both ways. So the 2 forces are what?
The vector and the friction force.
A vector and a friction force. Fair enough. You get partial credit. Friction force is correct. The vector, could you be a touch more specific? Velocity is a vector. Velocity is not a force. FGX, yeah, mg sine theta. That's what I was looking for. So, the sum of the forces in X, there is movement in the X plane, so we're going to use that. Sum of the forces in X is MA. Some people write MAX, but I know we're talking about X direction, so use it or not, it doesn't really matter. Then you have to ask yourself, so sum of the forces in X is MA. What are those 2 forces? Well, friction force and mg sine theta. Is that right? Are those the 2 horizontal forces? Yes. Which one has the minus sign in front? Friction force. Why?
Because it's going to the left.
It's going to the left. But it's going up as well.
But it's the horizontal front.
It's the horizontal. Exactly. When you turn it like this, it's to the left. It's clearly in the negative direction. Very good. So that's a minus, that's a plus. So MA is equal to minus mu sub k mg cos theta plus mg sine theta. Now, one of the interesting things that happens in this equation is that the m's drop out. There's an m in every term in the equation. So you can divide everything by m, and you're left with a equals minus mu sub k g cos theta plus g sine theta. Now, one of the things that we could do is factor out the g. And actually, I'm going to keep the minus sign in. And I get this. A is equal to g sine theta. I just move that up front because I like my positive terms in front of everything. And then mu sub k cosine theta. I find that the positive terms go up front makes it more aesthetically pleasing. It's just my personal thing. Now, the first thing about this A that we need to understand, and this explains more about how to problem solve, is that mass is not a factor. Mass, or wait, this equation is mass independent. I could give you the mass. I could have said this, well, in fact, I did say that this mass was 5 kilograms. But by looking at this equation, let me ask a question. If I double the mass, how does that affect acceleration? It doesn't. It's unchanged. It is mass independent. One of the things that you will learn from me is I have learned from my students that they are passionate plug and chuggers. They need to have their numbers. So one of the things I do to reinforce the fact that I'm in charge and make me feel better about myself is that sometimes I don't give the mass. And then people lose their ever-loving minds. And in the test, I'll have done the test already. So when you come to me and you say, this problem does not have mass, and my response is, and this is probably going to go on my tombstone, it is a correctly constructed problem. And you go, really? And all I say is, it is a correctly constructed problem. Now, who do I blame for this? Ryan. The Ryan rule forced me to become neutral. Because one time, I believed in helping people during tests. And so let's play you as the role of Ryan. Ryan had a question on his test. And he said, I have a question, because I don't want a person to just bomb out and get a 0 on the test. So he's talking to me, and he asked me, could I help him? And I'm looking at his problem upside down, and I gave him a suggestion which was horrible. And he crossed out his answer, which was correct, and replaced it with an answer that I nuked him. Took off like 20 points for the whole thing. He got very, very mad. And so what I ended up having to do was I had to become neutral. I'm your fan right now. I believe in you. But on test day, I have to keep everything balanced. And one of the things that I do with that is when I say let's say for this problem is on the test. You asked the question, you didn't give us mass, and my answer is it's a correctly constructed problem. What did I just tell you? You don't need it. So in a way, by not answering, I just answered. Very zen when you think about it. So just a pointer for the people in the class who show up. So I believe that there are three types of numbers on my tests. You get numbers because you need them. You get numbers that you don't need. Those are the devious ones. If I give you a number that you don't need and I see you plugging it in through a test, I know you don't know what you're doing. And then sometimes I don't give you numbers that you don't need, like mass in this case. So this is acceleration. Now, for just to figure stuff out, normal force is mg cos theta. M was 5, g was 10, cosine 30. So it's 43.30 newtons. The friction force, which is, did I say what the friction force was in this? Yeah, 0.2. 0.2 times 43.3 is 8.66 newtons, and A, 10 sine 30 minus 0.2 cosine 30. Okay. So the acceleration is 3.27 meters per second squared. Now this thing is speeding up. It has a positive acceleration. So will it stop before it reaches the bottom? No. Once again, one of my dumb questions. By the end of the semester, I want insolence in your voice. Just a little bit. Not complete disrespect, but just, how dare you, sir? That's what I want. So that was stage 3. Stage 1, give me normal force. Stage 2, give me friction force. Stage 3, get me A. Stage 4, work with the one-dimensional motion that we have. So x equals x naught plus v naught t plus 1/2 at squared, and v equals v naught plus at. At the top, we set our origin. So x naught is 0. We do have a v naught in this situation. V naught was 10, yes. So we know V naught and A. We do know X. And we don't know V and T. So the equation on the left is one equation, one unknown. This is one equation, two unknowns. We'll attack this. It's going to be quadratic. So 0 equals 1/2 at squared plus v naught t minus x. A is going to be 1/2 times our A B is equal to V naught, which is 10, and X, which is, what did I say X was? 20. And my TI-84 has an app for that. A, 0.5 times. Does it do math? Ooh, that'd be nice. All right, answers positive 1.59 seconds and negative 7.7 seconds. Negative time is not allowed. So we pick the positive time. Now, we've got our time. Let's get our velocity. V equals 10 plus 3.27 times 1.59. (15.2 meters per second). And you can box those answers if you want, but that works. So that is the typical motion problem when dealing with friction and you're dealing with two axes. Normal force, friction force, acceleration, motion. That's it. You're now prepared to do 6 of the 9 problems. Yes?
Like the question at the beginning was just asking for time and velocity, but as we're answering, you want us to answer.
It depends on what I'm asking for. I may have asked, like, give me the normal force, give me the friction force. It could be.
You would ask for that?
If I specifically ask for it, you've got to provide it. Now, if you write it down and I don't ask for it, I'm not going to penalize you for it. If I did not, I will say this. If I did not give you mass, like if mass was never given, I could not ask for normal force or friction force because mass is part of those equations. So if I said normal force, and your question was, well, what's the mass? Then I would be responsible for providing you a mass for that. Yes? How did I get what? Quadratic solution. The negative b plus or minus square root b squared, all that jazz. All right. Now, one of the things that you should be able to do as someone who has taken algebra and trig is you should be able to, maybe not with this one, definitely solve for any of the variables a, g, or mu sub k. In certain cases, you'd be able to, if this term wasn't here, you'd be able to solve for theta as well. But you should be able to manipulate these equations. If you can get to this equation and derive it, you could do any of these problems. It is the advantage that alphabet soup mode has over plug and chug. Alphabet soup is superior to plug and chug. The better students know how to do alphabet soup. We will learn why over the course of the semester. Now, this is the problem that will be on the test. Now I got everybody's attention. Funny anecdote or funny story while I'm doing this. I think it was the second summer session that that I taught 213. I stated just kind of off the cuff, there's an easy way to get an A in my course, which causes all the ears to perk up. And I said, bring me the head of Rebecca Black. And a third of the class, now it's too long gone. If you don't know Rebecca Black, I'm fine with that. But at the time, it was like 2 weeks after Friday came out, and it was just burning a hole into the internet. And a third of the class went, who? And a third of the class went, ooh. And the other third of the class went, oh, we're on this. We'll take her out for you. And yeah, I'm gonna change that mass. What do I make it? 7 kilograms. So this thing is at rest. I nudge it just enough so that it starts its motion and continues. And the question that I have is, how long does it take for it to reach the bottom? Simple question. You use the 4 steps that I've taught you. You sum the forces in Y to get a normal force. You find the friction force. You find acceleration. You solve for motion. This is as complex as it gets. Well, no, they're Atwood's machine problems that are horrible. But let me show you how to do this. We are very familiar with a number line. Minus and plus. Minus means to the left, plus means to the right. What I'm going to do is I'm going to take this axis and I'm going to bend it. So now the frame of reference is up here, anything to the left is negative, anything to the right is positive. But over here, anything down is positive, anything up is negative. All I did was I took the number line and bent it. The phrase that I use is, this is a loopy-droopy number line. So when I say left is negative, right is positive, up is negative, down is positive, that's perfectly normal. We should be accustomed to the fact that occasionally up is negative. Now in the, we need to talk about this thing. In fact, let me blow this up just a little bit so you can see it better. In this type of situation, that pulley is massless. There will come a day, a most awesome day, where I will finally make that pulley have mass, but not today. So don't worry about it. It makes your life so much easier if it's massless. I'm a giving guy. I care about the welfare of my students. So no mass in that pulley. Well, what does that mean? You've got to kind of think of these two masses as a system. They're connected and separate. You can think about this box here, and you can think about that box over there. In the horizontal plane for M1, let's draw the force diagram. M1 has a force down, which is simply mg. There is friction, boo friction, so we got to know what the normal force is in order to get the friction force. Now I put the friction force to the left because there is one last force, and that is tension. The tension in the string, if you only focus your attention on that one block, the block on the surface, like you're not aware of the rest of the Atwood's machine, as far as you're concerned, there's a string pulling this mass. That mass has friction and is under the influence of gravity. So there are four forces. Normal force up, gravity force down, friction force to the left, tension to the right. Now for something like this, if we just had this problem, well, you go, well, the 4 steps are easy. Sum the forces vertically, it's 0 because it's not moving in the vertical plane. That leaves you with normal force minus mg. So normal force is equal to mg. The mg just pulls over. Normal force is this. That's stage 1. Stage 2, friction force, mu sub k normal force, so mu sub k mg. Stage 3, sum the forces in x. Well, it does move in the horizontal plane. I need to fix this. This paper is bowing too much. Sum the forces in x. Since it is moving, you use MA, and I'm not going to differentiate AX or AY for a good reason. I'll let you know soon. That MA, there are 2 forces. Tension to the right. Well, we said tension to the right is positive, so positive T. We've said friction forces to the left, so minus friction force. So MA is equal to T. And one of the things that we need to really pay a close attention to are those masses, subscripts. So M1A is equal to tension minus mu sub K M1G. So let's go over what we know or don't know. We do know, oh my goodness, we don't know a lot of things. Or we do know just a few things. M1, mu sub K, we know we're on the planet. M1, but we don't know acceleration or tension. So we really can't go past stage 3 just yet. So what do we do? Well, we do the same steps on mass 2. Mass 2 is a lot easier from a force diagram perspective. Tension is up, M2G is down, and that's it. Now, question. What's the normal force on this block? And it's a dumb question. I like your answer because you said it with confidence, but it's wrong. I like whoever said 10, they answered. Actually, what did you say? Say it again. The right answer. There isn't any. Normal forces only exist if it's resting on something. So right now, this pin has no normal force. If I just tossed it up in the air, there would be no normal force. If it's suspended by a string, there would be no normal force. So you can skip 1. There's no normal force, therefore there's no friction force, so you can skip 2. So now you just move straight to number 3. The sum of the forces in Y is equal to M2A. And I still leave A as an unmarked acceleration. Now, in this diagram, you need to be aware, because it's the loopy-droopy number line, that up is negative and down is positive. So when you continue with your equation, negative t plus m2g. What do we not know? We don't know A, and we don't know T, but we do know M2 in G. So for these two equations, there are 2 unknowns. And now you die a little more inside because it's a 2 equation, 2 unknown problem. Well, let's handle this. In the with the idea that we're after the bottom line, I never really asked for tension. If I asked for tension, you would do this like a traditional 2 equation, 2 unknown problem. Since I'm more focused on the bottom line, which is how long does it take for it to reach the bottom, what we do is we eliminate t. We solve for t in one of these equations. Doesn't matter which one. Let's take a look at this one. So if I take equation 1, solve for t, m1a plus mu sub k m1g is equal to t. So now I have an expression for t. Let's plug that into this. Oh, thank you. So plugging it in to here, m2a is equal to minus m1a minus mu sub k m1g. So minus t is minus this. So the minus signs carry through. Plus m2g. And now what we have is an equation where there's only one unknown, A. So solve for A. M2A plus M1A is equal to M2G minus mu sub K M1G. Factor out A's and G's. A, M2 plus M1, G, M2 minus mu sub K M1. So A is G M2 minus mu sub K M1 over M2 plus M1. And that is the equation. For this type of situation, this is the derivation that you need to do. Now, it gets a little bit different in problem set. In problem set 3, this is basically what you need to do for problem 8. Problems 7 and 9 are a little bit different, but they are worked out in the tutorials. The other thing that I need to stress on, one is you need to know how to derive this. You need to know how to get to this point. Now, in the case that we have right now, let's continue with the problem. A equals 10, M2 7 minus 0.2, 0.4, m2 7 plus 0.4. So the acceleration is kind of boring, but (9.351) repeating meters per second. Or you could just write 9.351. Now, here's some interesting questions about that number. Should this number be positive? Yes. If it was negative, what would it do? It would go up and to the left, which would be kind of freaky. So in Atwood's machines problems like this, you can go ahead and pick that paper up. No one look at her after she dropped all the papers all over my floor. It's got to be positive. I'm not going in problem set 3. I think one of the problems, either 4, 5, or 6, it will have a negative acceleration, but it will not stop. In Atwood's machine problems like this, that thing is gonna have a positive acceleration. In this particular case, where only gravity is affecting the system, well, there's friction. But if there's no other forces other than what we've been dealing with, what is the maximum value of A? 10. So is it possible to get an answer of 12? No. The fastest this thing can drop is like this. 10 meters per second. Nothing can fall fast, or nothing can accelerate towards the Earth faster than 10 meters per second unless there was an external force applied to this thing, like a rocket. So if you do this problem and you come out with a number of 13 or negative anything, you've messed up. So when you look at the numbers during the test, that's a double check to see if you've done it right. To find the time, x equals x naught plus v naught t plus 1/2 at squared, it becomes a one-dimensional motion problem. A mass with a certain distance above the surface of 20 meters from an initial velocity of v naught accelerates downward at 9.351 meters per second. X naught and v naught are both 0. I declare the origin to be the starting point. So 2x over a is equal to t squared, and 2x over a is equal to t. So this becomes 2 times 20 divided by 9.351. I still have that number exact in my calculator, so I get an answer of 2.07 seconds. And that is the answer to the problem. Now, it's not really, if you get 2.1 or 2.2, I'm not that big of it, I'm not a fanatic about it. If you got 2 seconds, it's not going to be hurtful or anything. But what we're looking at is the procedure. And we can do things that test your knowledge of the procedure. What could we do to have fun? You call it a test, I call it a celebration. What could we possibly do with this problem that would test your knowledge? Well, let's say same situation, but I go, all right, M2 fell with the same situation. Length was 20, V0 was 0. Oh, and this is where the danger comes, because I gotta choose this problem so that it works. The time that it takes to fall to the bottom, instead of 2.07 seconds, took 8 seconds. So you have an object that fell 20 meters, and it took 8 seconds for it to do that. And it's attached to the same Atwood's machine that we had before. M1 and M2 are given 0.4 and 7, and I ask, well, what's mu sub k? Dun dun dun. So when you look at this, you go, it's a one-dimensional motion problem. Now granted, it's bent in half, but it's still one dimension. There is only one axis of motion. Couple of points. When I did this problem, I didn't differentiate the A's. There was no A1, there was no A2, there was no AX or AY. Y. And that Y is spelled WHY. Why were the A's not, why were there no differences or differentiation between the A's? Close. No. They're moving as one. They're moving as one unit. If one is accelerating at 9.351 meters per second, they're attached by a string. So the other one must move and accelerate at the same rate. If they accelerated differently, it would snap or it would bunch up. Not very interesting problems. The next thing, I didn't differentiate between the tensions. So the tensions must be equal. If I put mass on that pulley, the tensions would not be the same. And then there would be much crying. So that's one of the reasons why I don't put mass on the pulley yet. The tensions are the same, the accelerations are the same, the velocities are the same, because it's effectively one system. But for this part, you can go, well, if I know initial velocity, distance, and time, I can pop acceleration out real fast, because x is 1/2 at squared. I just took that equation and wrote it, cleaned it up. So 2x over t squared is equal to a. 2 times 20 over 8, 40 divided by 8, 5. Oh, I should have known that. So 5 meters per second per second. No, sorry, whoops. I would only take 3 out of 15 points for that. So give me partial credit. 5/8, yeah. 0.625 meters per second per second. Now granted, that is a rather small acceleration, but it's positive, less than 10, it's a valid number. Now that I have A, I look at this equation right here. I have my M's, I have my G, I have my A. The only thing that isn't available is mu sub K. You should be able to rip this equation apart and solve for any of the variables. M1, M2, G, all that stuff. What am I going to do? Divide by G. Subtract M2. Divide by negative M1. That means this line should go under that as well. And I'm going to clean this up. In fact, this is definitely wrong. Okay, so let's go over the steps. Here, divide by G, that comes down, that goes now without the parentheses. Minus 2 moves over, so that gets a minus 2 behind it, which is good. Now there's a minus M1 that goes under all of that, which is this. Now one of the things that you can look at and go, this is why I was sitting here going, what's this doing out here all alone by itself? The units of mu sub k are what? There are none. So A divided by G, an acceleration divided by another acceleration, gives you no units, which cancels. Mass plus mass plus mass gives you kilograms. Divided by kilograms gives you a unitless value. If it was like this, if it was like, let's just say for argument purposes, mu2 over m1 minus m2, which is nonsensical, the first part would give you a unitless value, the second part would give you a unit value, and then you would sit there and go, well, that can't be a coefficient of friction. So this gives you now 0.625 divided by 10, 7 plus 0.4 minus 7 over minus 0.4. Let's hope that the numbers work on this. Now, coefficients of friction, I said were typically 0.8, 0.2, something like that. This was very friction-y, 16.3, which is legit. I mean, think about, this surface is kind of sticky, but if you had like rubber with glue on it, the coefficient of friction would be very high. So it's a perfectly legitimate number. So that is an example of an Atwood's machine. What you need to do is you need to go through the basics of the 3 problems that I gave you in the problem set, go through the tutorials and review those, take a look at the old lectures that I may have gone through, especially this one that'll be posted up soon, and I will see you next week. Review session on Tuesday. Take a particular look at the summer of 16 test. Thank you.